Okay, my friends, we're diving in to chapter 6, though in truth we're actually even going back a bit into chapter 5. I had you do some reading last night that was dealing with chapter 6. 6.1 was talking about the development of the periodic table, right? And I ran you through the whole process, way more detail than we talked about. The focus is Mr. Mendeleev was doing atomic mass and periodicity, right? And our modern table is not atomic mass, it is atomic number and periodicity. Mr. Moseley, they talk about him as being the first person to discover this atomic number thing and deciding to order the table that way. But there's much more that went into this periodic table. We talked about this periodicity being this repeating pattern of properties. Say that 5 times fast, right? And we talked specifically about a few of them. We talked about atomic radius. Do you remember how atomic radius changes? As I move from left to right, what happens to it? Do you remember? From left to right, atomic radius decreases. It actually gets smaller as you get this way. And the reason for that is you've got more electrons as you move to the left. So the protons in the middle have more to grab onto, right? There's more protons in the middle, more electrons, so there's more electrical charge pulling them together, so they get smaller. Does that make sense? I add more electrons as I move to the right, more protons as well. How about as I move from the top to the bottom? How does the atomic radius change? It gets bigger, yeah. As I move from top to bottom, it gets bigger. Okay? By the way, these periodic pieces, more information about the trends, are located in chapter 6.3, which I did not ask you to read yesterday. I did put you a little note on Schoology about that. But they talk all about them there. If you want to see the sizes, it's on page 188. They show you the actual length of all the different atoms. You can check that out, sir. Of course, yep. I'll definitely put it up there for you, as well as the recording. They also, I included here about ionic radius. So remember, ions are when atoms give away or take on extra electrons. We've not talked about that much yet. This is from a previous year classes. So you know that the size does change. They show there's a little graph or a little table that's over on page 190. Don't necessarily worry about ionic radius. Let's talk about electronegativity, because we did talk about that one. Remember, electronegativity is how attractive electrons are, how the atoms are to electrons. Sir?
The second one is top to bottom, right? So it's not part of the atomic radius.
No, this is a different something. This?
Yeah. Was that connected to atomic radius or to the...
That's for atomic radius. Yeah. Right. As it decreases as I go left to right, it increases as I go top to bottom. This is talking about the radius of just an actual atom. This is talking about the radius of the ions that atom produces. I'm honestly telling you, just don't worry about it, truthfully. Yet. We'll talk more about it in a minute. It'll make more sense in a minute. Because we haven't talked about ions at all yet. Does that make sense? So don't even worry about the green part yet. We'll talk about it more. How does electronegativity change? Do you remember that from our conversations yesterday? If I move left to right, it increases, right? So it increases as I go left to right. So again, fluorine is much more attractive than lithium is. And how about if I go from top to bottom? It decreases, right? So therefore, lithium up top is much more attractive than francium down on the bottom. Cool so far? And last but not least, our ionization energy. How much energy it takes for elements to give off these electrons, right? To break one off. If I'm moving from left to right, that increases. So that tells me fluorine does not want to give away its electrons. It wants to hang on to them. And you'll see this more in a moment. If I go from top to bottom, that ionization energy decreases. So therefore, francium is much more likely to give away its electron than lithium is. Does that make sense? That's the summary of the lab we just finished with the cards, right? Of the pieces there's other pieces as well, but as far as properties go, I want you to be comfortable with those guys. And again, we'll talk about ionic radius. Don't freak out about that yet. It's always time to freak out later, right? Good so far? And again, this will all be up on Schoology, I promise. Good that you're writing it. Okay. So this periodic table, the groups give us information. Again, I mentioned this before, that we'll spend a whole day when we review for our semester exam just using the periodic table and all the different information that's present there. And the group numbers tell us something about the elements. The group numbers help tell us the number of valence electrons. Has anybody heard this term, valence electrons? Okay. Any idea what it means, or can you tell me what it means, Nathan? Cool. He said the top, which I hear where you're going for, outermost is what we call it, certainly. So you actually have an atom, and I'm using a planetary model here, right? If this is our nucleus here in the middle, right? Then you've got these different levels, right? And the group number tells me how many electrons are in that outermost level, in those valence electrons. So group number 1, how many valence electrons do you think it has? 1. Yes, you guys are smart, absolutely. 1 valence electron. I'm just calling it a VE. Okay? How about for group 2? 2 valence electrons. Okay? Now group 13, you got to cut off the 1, because it doesn't actually have 13 valence electrons. Okay? It has 3 valence electrons. You say, whoa, wait, Mr. Hess, what about groups 3 through 12? I say to you, remember yesterday we talked about those transition elements? They're like the back row elements. They're the ones that don't follow the rules. You know, like all those slackers in the back row in this room. Look around, you know there's slackers back there, right? What? Everyone looks at Rachel. Wait, what? Okay? Groups 3 through 12 don't follow the rules. I can't give you and say group 3 always has 3 or group 4 always has 4. It changes. We'll talk about the why to that. Okay? So we ignore them for now. We're talking about the main group elements, the representative elements from yesterday. They follow the rules. High school chemistry students love them because they behave. Right? Cool. We'll skip over to group 16. How many valence electrons does group 16 have? 6. So 6 valence electrons. How about group 17? 7 valence electrons. Good. How about group 18? 8 valence electrons. Group 14? 4 valence electrons. Good. And group 15? 5 valence electrons. So are you with me, friends? That the group number simply tells you how many valence electrons there are. And you say, whoop-de-doo. Who cares? Valid question. What if I told you it's the valence electrons that do all the reacting when elements react together? The guys in the middle, they're not affected. Rarely. It's the valence electrons that either get taken away or given to somebody else or shared together. So those valence electrons determine how these elements react. Are we cool? Sure, the ambassadors is a great way to think of them. Okay? So that's why we'll talk a whole bunch about these guys over the course of this year. And I want to show you how you can determine how many of them there are, because that makes a huge deal. We're cool so far? Valence electrons, pretty straightforward. Okay. So now these valence electrons do 2 different things. Either they are given away or they are received. Are we cool? If I give away a negative electron, that atom now becomes a positive ion, right? It gave away a negative, so it's a positive. If I accept an electron, now I have more negatives than I have positives, right? More electrons than protons, so therefore I become negative. Does that make sense? And here's the key. Everything wants 8. It wants 8 valence electrons. Every element, other than 2, wants 8 valence electrons. That is the goal. Oh, that's so heavenly. If I can get 8, I'll be so happy. I'll be so cool. Then I'll be like the noble gases. And if I can just be like the nobles, oh, life would be so much better. Right? Right, Alex? Of course. Alex shakes his head no. Okay? But elements want to be like the noble gases. That's their key. Right? And we'll learn more about the why. But trust me on this one. Okay. I do that to set all this up. Group 1 has how many valence electrons? 1. So if it has a choice, it can either give away 1 electron or it can accept 7, right? Because it wants to get 8 in its outermost level. Which do you think would be easier? It's going to give away 1, right? Sir? It's just easier. Because remember, underneath, we're talking only valence electrons. Underneath, it has already 8 in its underneath level. So that'll make it happy. If I just give away the 1, now it has 8 in its outermost level. Does that make sense? It's a good question. It's a valid question.
So once it gets rid of that valence electrons, those 8 become valence electrons?
Right, because now they're the outermost. Perfect. So therefore, if it gives away 1 electron, what charge will group 1 have? It'll be an ion. What charge will that ion be? A 1 plus, or a positive 1. Doesn't matter which way you put it, plus 1 or 1 plus, doesn't matter. Does that make sense? It's weird because it lost an electron, but it's a positive number. That seems weird, I get that, math-wise. But it's because it lost a negative. And 2 negatives make a positive, right? It lost a negative something. We cool? How about group 2? Let's use your brains. What charge do you think that's going to be? 2 positive. Because again, it can give away 2 or it can accept 6. It just makes sense. It's going to give away 2, right? Does that make sense, David? Much easier just to give away those 2. Continue the pattern. Group 13, what do you think? It's going to give away 3, so it'll be 3 plus, or positive 3. No, it's going to give away 3. Because again, otherwise it has to accept 5, right? Easier to give away 3 than it is to accept 5. No worries. Okay, let's skip 14 and 15 for a second. Let's talk about group 16. Group 16 is how many valence electrons? 6. It needs 8. So it can either get rid of 6 or it can accept 2. Right? Does that make sense? So therefore, what charge do you think this is going to have? Negative 2. Beautiful. Okay? How about group 17? It has 7 valence electrons. It can either give away all 7 or accept 1. It's going to accept 1, so its charge? Negative 1. We're cool so far? Okay, making sense? How about group 18? How many valence electrons does it have? 8. So it's happy, right? Does it want to give away electrons? Does it want to accept electrons? No. They are noble. That's where this name comes from. They're like the kings above everybody. No. No, I don't need to interact with you people. Not that that's how nobles are, but that's the thought, right? Alex just loves chemistry class now. Are you with me, friends? So what will the charge be for group 18? It'll be 0. It doesn't want to give away charges. Okay?
Could you explain the 16%?
Group 16 has 6 valence electrons, right? And it wants 8 total, right? So it can either give away all 6 to have a full shell underneath, or it can accept 2 more to get to that 8 number. And it's just easier to accept 2. And since we're getting 2 negatives, we make it a 2 negative charge. Okay, I broke out group 14 and 15 because of this. Many times, if you look at the PT, we do have a lot of metals in group 13, right? But in group 14, can you see there's just lead, there's tin, and then I've got 2 metalloids in silicon and germanium, and then 1 nonmetal in carbon. So group 14 is where we've really got a lot of different things together. So these guys on the bottom, tin and lead, they can give away all 4 of theirs, but they also tend to share. That's the other thing we didn't talk about. Electrons can be given and taken, or they can be shared. And those are covalent bonds, exactly. Normally, they share. So they very rarely will give away those all 4 of them. Again, tin and lead at the bottom, they actually sometimes give away 4, sometimes give away 2. It depends. So we kind of just ignore those guys. Does that make sense? So if we had to say something, we would say this would be a positive 4. Actually, sometimes it's even a positive 2. But normally they're just going to share. Carbon will always share. It will never give away its electrons. It always shares. Well, I guess I should never say never, because you can always make something do something, but rarely. Okay? Group 15, you see, is again one of those mixed groups, right? 2 nonmetals on the top in nitrogen and phosphorus, 2 metalloids in arsenic and antimony, and 1 metal in bismuth. There's actually also a metal down here in period 7, but it's not on the PT here. That's old. So if it has to react, what charge do you think those metals would have? It would have a +3. Oh, excuse me, a +3. A -3, right? It would take on 3 electrons. So that would be like what nitrogen and phosphorus do. But truthfully, bismuth down here can be a +5. It can also be a +3. Again, there's some weirdness to it. That's why I kind of put those 2 down on the bottom. But 1, 2, 13, 16, 17, 18, those are always going to be the charges that are listed there 99 times out of 100. Make sense? Questions there? And again, do you have to memorize this? No. Well, yes, but it's on the periodic table. Right? As long as you understand that those group numbers give you that information, life is good. Yes, ma'am. Group 14 is because it's 4, right? So it wants 8. It's kind of like stuck in that halfway in the middle. Plus, remember, group 14 has got nonmetals, 2 metalloids, and 2 metals. So each element kind of does a different thing in group 14. These guys down the bottom, tin and lead, they will usually give away their 4 valence electrons, or even sometimes only 2 of those valence electrons. They kind of act like these transition elements who give away multiple numbers. But the nonmetals up on top, group carbon in group 14, it'll share exclusively. It doesn't like to give away electrons. So it just depends on the element. That's why I put it down the bottom. There's not a nice, easy, comfortable rule for group 14 or really for group 15 either. Sir, you can't possibly wait till we're done? 15 minutes? Appreciate it. Are we cool here? Whew. It's a lot of conversation, Jason. I apologize. All right, let's talk about energy levels and sublevels. All of this is to get to the electron configuration piece that you read about last night. A lot of background, right? Yeah. No worries. That's why it might have been a little bit confusing as you were reading. Energy level is the same thing as periods. I want to make sure you understand that. Energy level means periods. What we're doing is we're saying, if here's the nucleus, the first energy level, the second, the third, the fourth, etc. Away from the nucleus. And again, we're thinking like a planetary model, even though we know it's actually electron cloud, but it's easier for us to draw a planetary model. Okay? So how many electrons does this first energy level hold? It holds 2. You're exactly right. Question? So far we've only found 7, but we've filled up 7. Like if we were to find any more elements, it would be in the 8th period. But as of now, we've not found anything yet. It's just too unstable. At that point, they're so big, it doesn't like to stay together. It breaks up into smaller pieces. Decay, right? Radioactive decay. They won't stay together. It breaks apart. How about in period 2? How many electrons will that one hold? Not 6 is close, though. It is 8. How about in period 3? Oh, nicely done. 18. And periods 4 through 7. I'll get your question 1 second. Period 4 through 7 holds? Not 8. Anybody? Not 20. 32. 32. Your question, sir? All we're doing is simply calling this 1, 2, 3, 4. I'm just telling you how many electrons it holds. We'll talk more about how you can see that in just a moment. Ah, see, now you're good. It's good. Remember, we're talking about 8 in its outermost to be happy. So not only 8 total, but just in its outer. Oh, yes, I hear you. We'll talk more. I promise. I promise. It's good. It's good. Sir, quick. Be quick, quick. Okay? You're good so far? Because I was tossing numbers at you, and I'm going to show you how it actually works together. Inside these energy levels, there's actually sublevels. Think of it this way. It's like a hotel, right? A hotel has got floors, but then those floors are divided into different rooms. Does that make sense? But in our atom, the first floor, the first sublevel is called the S sublevel. The second one's called the P. The third one's called the D. The fourth one's called the F. Why those letters? I didn't make them up. I don't know. That's just what they picked. How I remember them are some people drink Frappuccinos. You can come up with whatever name you want, but that's how I remember it. Some people drink Frappuccinos. Maybe I should say smart people drink? I don't know. Frappuccinos, but yeah. That's my favorite Starbucks drink, I must admit. Nice Java chip Frappuccino. It's like 1,000 grams of sugar, but man, is it tasty. We good? Okay. And each of these sublevels hold a certain number of electrons. You ready for some more numbers? Yes. Here we go. S holds how many? Anybody? 2. Good. P holds how many? 8. Oh, nope. Not 4. Good. D. D holds 10. And you see the pattern? I add another 4. And yes, these are all electrons. Dropping markers. Electrons, 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 right? 2 electrons, 6 electrons, 10 electrons, and last but not least, 14 electrons. Whew. Almost there, Josh. We good so far?
So, all of these sublevels are within
each energy level?
Yeah.
Good question. No. What they're going to do is they're going to put electrons into sublevels until they're full. Here, let me show you. In energy level number 1, how many electrons does it hold? 2, right? So therefore, both those electrons will go into what sublevel? The S. So this first energy level is all just S. I'm trying to draw in, but my marker is just off enough to mess it up. So we would call that the 1S. 1 is the energy level. S is a sublevel. We cool? For the second energy level, how many does it hold? 8, right? So therefore, the S is like divided in, the energy level 2 is divided into 2 pieces, right? we have the S sublevel, and we have the P sublevel. S holds 2. How many does P hold? 6. 2 plus 6 is 8. Oh, I'm seeing light bulbs. That's good. We'll keep going. Shh. Shh, shh, shh. Stay with us. Stay with us. Some light bulbs have gone off. Others have not. So hear me. Shh, shh, shh. Yours is not burned out, I promise. This is my 2s. This would be my 2p. Right? In the second energy level, there's both an S and a P. Because it has to hold 8 electrons total. 2 in the S, 6 in the P. How about in energy level 3? How many electrons? 18. So therefore, it's going to have an S, it's going to have a P, and a D. So it's going to break into 3 pieces. Shh, shh, shh. Stay with me, guys. An S, a P, and for the first time, a D. Right? And this is my 3S and my 3P and my 3D. And you see where we're going next, right, friends? Okay? That the 4th as well as the 5th and 6th and 7th energy levels, they have all 4 sublevels. That we have an S sublevel, we have a P sublevel, we have a D sublevel, and last but not least, we have an F sublevel. So for F, for S, for P, for D. Maybe, potentially, theoretically. And again, we can keep that going. 5 would be just like 4. 6 would be just like 4. 7 would be just like 4. Casey, have you ever found that 8 sublevel? It would be just like that. Theoretically. Because we haven't actually discovered it. Theoretically. Is the brain hurting yet?
Yes.
Good. You're thinking. This is good stuff. Yes, sir.
So the valence electrons be on the outer ring?
Always the outermost level. Where they are depends on what element it is.
Okay. But on this one, would it be even further?
So in what I've drawn you here, the energy levels that would be in the 4th energy level, the electrons there, those would be the valence ones.
Out of all the electrons.
It's just whatever is the outermost.
Okay.
Because then again, each element has different amounts. That's what we're getting to, friends. Shh, shh. Is that each element has different valence electrons. Their electrons are in different spaces. We'll talk about how that's what electron configurations show, where the electrons are. Are you with me? Okay. I'm telling you tomorrow, I want to give you a little bit of a quiz on the periodic trends, this stuff, right? Not the green stuff, blue, red, black. I want to give you a quiz about the number of valence electrons in each group, right? As well as the charges. I'm not going to quiz you over the energy levels and sublevels. Tomorrow. Maybe some extra credit. Yes, ma'am. Please, it'll be up on Schoology as well. But you, oh, this? Yes. Sure, sure. Formative assessment quiz, formative assessment, yeah. Are you with me, friends? In 4 minutes, let's go on, because I'm going to show you how we actually use these. Here's the point. I can take this and I can now assign each electron from an element into a sublevel. And I can write what you read about last night called an electron configuration. It would look something like this. 1s2, 2s2, 2p6, 3s2. These top numbers tell you how many electrons are in that sublevel. That there are 2 in the 1s, and then it's full, right? Yeah. There are 2 in the 2s, now it's full. There's 6 in the 2p, now that's full. 3s fills itself up. What element would that be? Can anybody tell me? that its last electrons go into 3s? Any guesses? Close. Magnesium. Magnesium. Whew. I think we'll stop there. Because if you count them, right? 1s2, 2s2, right? It fills up both. 2p6, 3s2. Do you notice, by the way, that there's that many periodic table squares in each section? Whoa, I saw some good light bulbs right there. Again, we'll talk about that more tomorrow. We didn't get a chance to get to it today. What I'm telling you is, here's my point, and then I'll stop. All of this right here, this whole entire graph is encapsulated right here. You don't have to memorize it. If you understand how this works, you already have that memorized. Okay? So again, quiz for tomorrow. I would love it, friends. I would love it, and I'm sorry to keep giving you so much reading, but there's good stuff here. I would love it if you were to check out, it's actually 5.3. Making sure I'm giving you the right piece here. Yes. So reading 5.3. Okay? Whew. Lots of good stuff. Adios, friends.